So why are we doing all this? So it takes some computations to do the eigenvalues and the eigenvectors, but Maple is rather good at doing that. There is a command called Eigenvectors. Look at the Maple demo of today, and you will find out how easy it is to actually compute these things when you use Maple. But in order to understand what you're doing, I am doing this at the blackboard, and you will have some exercises where you're going to do the same thing this afternoon. But in the future, then you will use Maple, and things are really easy. But why do we need these eigenvalues and eigenvectors? And the answer is that if you have linearly independent eigenvectors enough, if you have enough of them, then they form a basis. And if you have a linear mapping, then this mapping becomes, or the mapping matrix becomes especially simple in that basis. And I'm going to show you now how this is done. And the question is, can we diagonalize a matrix? So we are given a linear map F, and it is from Rn into itself. Say, you can represent it by a matrix. And now we assume, so this is an assumption, but we assume that F has n linearly independent eigenvectors. Let me write it here. So, and we call them E1, E2, up to Vn. And if I write it, so when I use my function on V1, I get lambda 1 E1. I get lambda 2 V2, and so forth. I get lambda n better. Shift to that one. Now, all these lambdas are not necessarily different. We saw an example with a 3 by 3 matrix where the algebraic multiplicity of lambda 1 equals 1 was 2. So, but luckily, the geometric multiplicity was also 2. So you had 2 linearly independent eigenvectors corresponding to lambda 1 equal to 1. But this assumption is not always true. So you cannot always find n linearly independent eigenvectors. But now we assume that we can. And then we simply choose v1, v2, or this as a new basis. And this is possible because you know that n linearly independent eigenvectors, they span Rn. So this is possible. Let me write the equations I have put up here, where I take the images of the basis vectors. You know, if I'm going to have the mapping matrix, then I have to, for each column, I have to write the image of the basis vectors. So the image here is lambda1, but then it's with 0, and it's 0 all the way through. And if I take the image, I get 0 times v1 plus lambda2 times v2 plus 0 times vn. And I can continue this, and I get f 0 times plus lambda n times vn. So if you look at in this structure here, if you look at the diagonal, you have something, but elsewhere you have 0. So on the basis of this, I can immediately write down the mapping matrix where I use this eigenbasis here, V, as basis vectors. So this mapping matrix is simply lambda1, 0, 0, lambda2, and then 0, 0, 0, and then lambda n. So if I choose the eigenbasis, then I get this simple equation here. Now, normally you don't have, if you're looking at a given mapping matrix, you are not in the eigenbasis, but you are, say, in the ordinary base or some other basis. But to get to the eigenbasis, you have to shift basis or change the base. So if I should change the base from V to E, this is the one I can most easily write down. I have to have as columns the E coordinates of the eigenvectors. And but if you have found the eigenvectors, then you also have these coordinates in the given basis. So what I can do now is that I can write down the mapping matrix in the e-coordinates, but if I have found this mapping matrix, say in the with the eigenbasis, I have this mapping matrix. So I have to shift from E to V, and here I have to shift from V to E. So if I pre-multiply by this one, this is the one I have written down up here, and then I post-multiply by this one, which is the inverse of this one, I get the ordinary matrix. So if I write this, normally when you have a problem, you just call the mapping matrix for A. So this is my mapping matrix in this basis here. These are the e-coordinates. I use a capital V in order to represent the coordinate matrix in e-coordinates of the eigenvectors, called V. And here you have a diagonal matrix with all the eigenvalues. And usually you use a capital lambda. This is a capital lambda, the Greek letter. And then the last one here is simply this one, or the inverse of the first one. So if you have a matrix and you find the eigenvalues and the eigenvectors, then you can factorize the matrix in this fashion. You can also write it, you can have an explicit expression for this matrix, this lambda matrix, because you can pre-multiply this equation by the inverse of V and post-multiply it by V. By the way, is this allowed? Is it even allowed for me to write the inverse of V? Does it have an inverse? It's a matrix of the n eigenvectors in e-coordinates. Yes, because I assumed that you have n different or linearly independent eigenvectors. So this is a regular matrix, and it has, of course, an inverse. So you can do that. So let me multiply A by this one, then you get the identity matrix. And here, and if I post multiply it by V, I get this one. So if you have found the eigenvectors and you have your matrix, you can just multiply in this fashion, multiply A in this way, and then you get the diagonal matrix. What I'm going to end up today with is that I'm going to show you a nice way of using this. Because what I'm going to do is that I'm going to show you how to compute the power of a matrix. The power of a matrix. And let me just repeat this. Or I have A is equal to let me just repeat this. Now, we assume that A has the eigenvalue lambda. Now we can pre-multiply this equation here by A. You have A times x plus or is equal to lambda, and then I should write it like this: A times lambda x, and I can write this as A times A. I can write it as A squared times x, and here I can interchange the lambda. I can put it outside, and then I get A times x. But since lambda is an eigenvalue, I can replace A times x with lambda x, so I get lambda times lambda x, so I get like this. And what does this tell me? It tells me that lambda squared is an eigenvalue of A squared, but it has the same eigenvector as the original problem. X stays the same. I can continue this, say, to some power m, and then I get lambda m. That is, I get for this matrix A to the mth power, I have that lambda to the mth power is the eigenvalue for that matrix. Now, I'm going to return to the example. I have 5, 3, minus 6, minus 4. And I have lambda 1 equal to 2, and that corresponds to the vector 2, 1. And then I have lambda 1 equal to minus 1, and this corresponds to the vector 1, 1. So if I write this factorization of my matrix, it looks like this. I get 5 minus 6, 3 minus 4 is equal to my my V matrix, which is the coordinate matrix for my eigenvectors. So that will be 2, 1, and 1, 1. And then I'll get my diagonal matrix with the eigenvalues, and that will be 2, 0, 0, 1. And then I have to multiply by the inverse of this matrix here. So the determinant is 2 minus 1 is 1. So the inverse I have to divide by the determinant, but this is 1. And then I have to interchange these two, 1, 2. And then I have to change sign on these two. So this is the inverse. There's a formula in the e-notes for that. So this is A, this is V, this is lambda, and this is the inverse of V. And the question now that I want to solve is that I want to find the 10th power of A. Even though it's only a 2 by 2 matrix, if you should do it by hand with only these matrices, it will take you some time to do the computations. But see what we can do now. Because this is simply what I showed you up here is that the powers of A have the same eigenvectors as does the initial A here. So I can write this as where I have, say the eigenvectors here and the inverse of that matrix. So what I need to do is I only need to calculate the 10th power of this diagonal matrix. And let me do this. And if you do this, you will realize that you take the power of a diagonal matrix by just taking the powers of the elements in the diagonal. That's one. But this is an error. Or is it? I don't know. But the result is the same. So let me just state this. Because when you then get the power here, you get and this is 1. So this is the power of the diagonal matrix lambda. And then if I multiply in front with the matrix with the eigenvectors, I get 2, 1, 1, 1. And then this matrix 1, no, 0, 0, 1. And here you get 2048. And here you get 1. Here you get, and here you get a 1. Then I have to multiply this result with the inverse of the, and this is this matrix here, so that is 1 minus 1 minus 1, 2, and you get like 2047. I have to subtract 1 from this number here, and then you get minus plus 2, that is minus 246. And then you get 23, and then you get minus plus, that is minus 222. So I should have put in here, because it's the 10th power of A. So this is the result. This is not the main usage of diagonal matrices and the eigenbases, but you will find out about this afternoon when you do the exercises. And today, please look at the GeoGebra exercises, because you can learn from them. Okay, see you this afternoon. Thank you.